In today's video, we're going to be talking about nuclear energy. After watching this video, you should be able to understand the difference between nuclear fission and fusion, and understand how we can use nuclear energy to create electricity, which is something that we're looking more and more into in terms of trying to get away from coal-fired power plants and maybe looking into more of the nuclear side of energy. So let's get right into it. Nuclear fission, the thing I remind you to think about is fission is division. This basically is when an atom is splitting. And why it splits is usually a neutron is needed to smash into this unstable nucleus of an atom. That neutron that smashes into that nucleus, basically it makes the atom more unstable than it originally was, and thus causes it to undergo fission. And if you think back to the previous lessons, basically the strong force is not able to keep that nucleus together, and all of a sudden it starts to split. So basically you get two new atoms that come from this one big atom, and while it splits, it releases typically energy and a few extra neutrons that then are able to freely go about and do their business. Okay, so that's what fission basically is you have a big atom, it splits into smaller atoms or fragments, and it releases some energy along with some neutrons into the surrounding space. Typically for nuclear power plants, they use something called uranium-235. Uranium-235 is not real stable to start with, but what we do, or what nuclear physicists do, is they shoot a neutron into the atom of uranium-235. And so with one more neutron, it now becomes uranium-236, which is super unstable. So uranium-236 then undergoes fission into barium-141 and krypton-92. During this fission process, it releases energy and sends out 3 more neutrons. Okay, so you have this big uranium-236, it fissions into barium and krypton, and then you also get a release of energy and 3 more neutrons that are released into the surrounding area. This fission is responsible for what generates nuclear power at nuclear power plants, and also can be used to create atomic bombs. Okay, so pretty big deal. This is just a picture showing what I was kind of talking about here. Here we have the symbols for one neutron. So here you have one neutron, and it's going to be smashed into this uranium-235 atom right here. Okay? If you smash this in it, you get uranium-236 just for a second, and then all of a sudden it undergoes fission. And here's barium, here's krypton. Here are 3 individual neutrons that are just released into the surrounding area, plus some energy. And that energy right here is what is being used by nuclear power plants, or on the more scary side, atomic bombs. Okay, you get this large release of energy because you have more than just one uranium-235 doing this. You have hundreds, if not millions, of uranium-235s undergoing fission in a split second. You have all this energy being released. So if you consider the example in the previous slide, how you have uranium-235 being smashed with a neutron and undergoing fission, and you think about those 3 neutrons that are released, what if you were to put other uranium-235s nearby that uranium-235 that just got hit with a neutron? What would those 3 neutrons do? Well, what if they hit another uranium-235 in the area? And that uranium-235 now undergoes fission. So all of a sudden you get something called a chain reaction, where basically you have a neutron hitting uranium-235, it gains that neutron, it splits into fission, and then you've got 3 more neutrons released, and they go out and they hit another uranium-235 to then undergo fission. 3 more neutrons are released, and it just continues to go on and on and on. This is called a chain reaction, and if you get it enough uranium-235 in an area, you can have this go on as long as you have enough uranium-235 going. And so that's basically what a nuclear power plant is doing. It's using this idea that once you get the reaction going, it just continues to self-sustain or keep itself going. Now this is what's kind of scary too about nuclear power plants, is this chain reaction can get out of control, and that's not good either. Okay, so it's a fine line that you walk between a good chain reaction and one that basically is out of control. So basically, a nuclear reactor is basically a structure that stores these unstable atoms capable of undergoing fission. So in our case, uranium-235. When an atom undergoes fission, it releases a ton of energy, and then that can be used to do useful work. And we'll kind of talk about what useful work can be done. There are three primary challenges to kind of keeping this chain reaction going, this fission going. The first is the neutron velocity. That first neutron that scientists or nuclear physicists will shoot into the uranium-235 has to actually be moving at very low speeds, or else the uranium-235 won't accept it. So it has to be moving very slowly when it collides with the other uranium. When it collides with the uranium. Then the other challenge is once that uranium-235, so maybe I'll draw a little picture up here. Here's this uranium, I'll call it U-235. It undergoes fission, and now you have 3 more neutrons that are released, okay? And they're on the hunt to find more uranium-235, if you will. These guys are moving super fast, okay? They're moving super fast when they are released undergoing fission. So how do scientists undergo this or solve this problem? Basically, they add in what's called a moderator. And a moderator is an atom that has a mass that's very close to the mass of a neutron, and they slow the neutrons down. It just so happens that hydrogen, it has 1 proton and 1 electron, which in this case we can assume the electron's massless. But if you remember, protons and neutrons, they're pretty close in mass. So if we put a hydrogen atom here, or actually a lot of hydrogen atoms here, these are all moderators. And when these neutrons collide with the hydrogen atom, they get slowed down. I kind of like to think about pool. If you hit the cue ball into another pool ball, basically the cue ball is going really fast, it hits the pool ball, bam, the other pool ball moves, and the cue ball has slowed down considerably, if not even almost stopped. Okay, so that's what a moderator does. It slows the speed of neutrons down to allow this chain reaction to occur. The second is neutrons don't always go in the direction you want them to go, right? They may just actually leave the nuclear reactor, okay, and not strike any uranium-235. So the way scientists have fixed this is basically they've enriched the uranium. They're going to make it so that there is more uranium-235 present. This almost just seems like common sense, but it's a good way to fix it if you think about it. Just put more uranium-235 in the area so that there's more opportunity for these fission reactions to occur. The minimum amount of mass needed for this chain reaction to kind of sustain itself is called the critical mass. So basically, when you hear about enriching uranium, what they're doing is they're getting a lot of uranium in an area that's unstable that can then undergo fission. The third problem is certain uranium isotopes can also absorb the neutrons and react, but not react in a way that you want them to. So there might be, various isotopes of uranium in the area. The way we fixed number 2, or the previous slide, is the same way we're going to fix this one. Just making more uranium-235 present in the area, and you won't have a problem, or as big of a problem. You have the right type of uranium isotope present to be able to basically keep that chain reaction going. So this is a little diagram of a nuclear power plant. So let me get my pen out here. Here is the nuclear core right here. And basically what's going on is you've got these fission reactions going on. And this is really hot, okay, because there's a lot of energy being released in the form of heat. That hot heat basically heats up this water. And that water then is moved into this chamber right over here, where basically it starts to evaporate. And that water vapor then causes this turbine over here to spin. If you have a spinning turbine, that can then make electricity. Okay, you can make electricity through a spinning turbine. Electricity. And then that electricity can be used in your homes and whatnot, which is basically the same principle of how a coal power plant works. Basically, they burn the coal to heat the water to cause a turbine to spin. Basically that's what's happened here. Instead of using coal, though, we're using nuclear reactions to cause this turbine to spin. So what does the water do once it's gone through the turbine? Well, it then cools and condenses in this condenser back to normal water again. Okay, and so it goes down here, and then it gets pushed here over here by a pump, and then move that back into the nuclear, or the area where the nuclear core is, to then be reheated and keep the process going. So it's basically, in a nutshell, I mean, there's a lot more technicality to it if you were looking at a deeper level, but for our basic understanding of a nuclear power plant, this is what goes on. That nuclear core heats the water up. The water then evaporates, spins a turbine, which then makes electricity. The water condenses and gets reheated up again. The process repeats itself. This is basically what I was just saying in text form. Okay, so the core contains fuel and moderators, which undergo fission and release energy. That energy is used to heat up water, and that water basically rotates a turbine, and that generates electricity. And the water then is cooled and repeated and reused again. So kind of a neat way to create energy versus burning coal. The other type of nuclear process, if you will, to compare to fission, is something called fusion. Fusion is when you kind of put together, I have on here, to fuse or weld things. Basically what that is you're putting small atoms together to make larger ones. During this process of taking basically hydrogen atoms and melding them together to make helium, you release a ton of energy. This, though, requires much, much higher temperatures and pressures, things that we are really unable to find or sustain on Earth. And so this is why it's kind of out of a human's reach, really, to undergo fusion in a large scale. Because this is actually what happens at the center of stars. So if you were to look out at the stars at night, the reason you're able to see light is basically you have fusion going on in those stars up in the sky. That takes care of this video. I will see you guys next time.